Hello all, welcome to Techno in the series of artificial intelligence. Today's topic of discussion is hill climbing. So hill climbing, here we'll look into, it's also known as local search algorithm, local search algorithm. Uh, we'll look into the greedy approach of it. Use greedy approach of hill climbing because I'll just get into it why we call why we use greedy approach, like why we tell that we are using greedy approach over here, and then there is no backtracking. Okay, so basically what we are doing is I'll just show you down over here that we'll be when we are using hill climbing, just imagine that you are visiting somewhere on hill station and you have to climb up. So till you reach the maximum point of the hill, you go moving forward, right? And then you stop to view the peak. Now similar is the case of hill climbing. All the instances will look into the each cases until they find the local maxima, they'll operate, and then when they find local maxima, they'll stop the algorithm there. So it's local search. Why it's local search? Because it's finding local minima, local maxima. Why we are talking about local maxima? Because in hill climbing, if you have like this, if you have approach like this, graph approach, and if you reach over there, here, this point, this is local maxima. And if you still have the global maxima over here, means the optimum answer is here, but you have reached one typical point. After that, you have to lower down. Then the search algorithm will stop here at this point. So we call it as a local search algorithm. Then why greedy approach? Because we don't want the optimum solution, we want the accurate and the first solution that we get. That's why I use a greedy approach. And then we don't go backwards in this direction, or we don't go steep into this direction. Like after coming up, we don't go down, and that's why it's no backtracking. Okay, so these three words, I think it should be clear to you. Now we'll look into how to evaluate a hill climbing program. So hill climbing problem. First, we evaluate the initial state. You can note the steps down. Evaluate the, I'll just note it in the color so that it's visible to you nicely. Evaluate initial state. After evaluating initial state, you have to loop until, we have to keep checking the states until a solution is found. A solution is found. Or there are no operators left. We have to iterate until we don't have any more operators, or we find a solution. Now we have to select and apply a new operator. Then evaluate that new state. I'll just give an example in a second. So if you don't understand what I'm saying, just wait. Okay, but this is the way that you solve this. Then evaluate the new state. So till when we have to evaluate the new state? If goal is found, then quit. If it's better than current state, it's better than current state, then it's the new state. So what we are trying to say is that you have to start iterating states, and you have to take one step, one state at a time. You have to start with the initial state and then iterate till you have the operators left. When you have no operators or you get the solution, you have to finish it. Now, if you find the goal state, then you have to quit the algorithm. If you don't find the goal state, then if the current state that you are working with is better than the previous state, then we say that it's the new current state. Okay, so let's just take an example that I have a node of solutions. Okay, I just have like 3 branches to it, and let's just say that, okay, so this is initial state, and I want to find the max possible, like best possible way to reach to the goal state. And so like this, sorry. Okay, so what I find over here is that after I start from here, this is the best way. So we'll take this way and not this way. I'm just saying, for example, that if I found that, like say 1, 2, 3, 4, so second way is the best way, so I'll take up that way, and then I'll again check all the branches or all the nodes of that, and again find the best way to reach. We'll look into one problem of 8 puzzle problem. I'll just give a short example to make you understand what exactly I mean to say. Just give me a minute. Okay, so let's just take this example over here. I'm having 1, 2, 4, 5, 7. In case you can't see, I'm speaking, just bear with it. 3, 6, and 8. Okay, this is our initial state, and what we want is, a little bit bigger. One, 4, 7, 2, 5, 8, 3, and 6. Okay, this is our goal state. This is what we want. This is what we have. Now, what we'll do, we'll turn out all the cases. Okay, just for example, say that I took 3 cases over here. Of 8 puzzle problem. What do I mean by cases? There will be more, but I'll just take the 3 for example. Now let's say that I want this empty space over here, right? So for the first step, I'll move this empty space towards the left hand side. So 1, 2, 4, 5, 7, 3, 6, 8. This is our first step. And then let's say move this towards right side. So 1, 2, 4, 5, 7, 3, 6, 8. And then maybe I'll just push it down or push it up. So 1, 2, 4, 5, 6, 7, 3, and 8. I pushed it down. Okay, so like this is my second state, this is my third state, and I'll have more such states possible for up, down, left, right approach. Okay, now I can see over here that 1, then 2, then 4. and 3 sets are here like this. So 8 can be over here. So I'll just go with this state that okay, this state can have this many. Again, some solutions over here. This can have some solutions over here. So I'll go with the case looking into the goal state. I'll just take like which is the optimal solution that I think will be, and I'll go one by one. So whichever is better state, I'll make it as a current better. See, if I see that okay, first state is better than the initial state to reach the goal state, then I'll opt the first state over here, and then again move to its branches, and then again check one by one which one is better. So this is actually the somewhat the main focus of hill climbing. Okay, I'll just erase it from here. Okay, we'll look into the problems of hill climbing. So you might be wondering where actually hill climbing is used. Then majority of the times 8 queens problem and TSP we use hill climbing. So let's just say, yes, I'll just write it over here. I'll just keep it blue only. Oops. Okay. So now we discussed what is hill climbing, why it's local search algorithm, greedy approach, no backtracking, what actually is hill climbing, and how problems are solved using hill climbing. Now, any problem solving technique has some problems with it. Then only we evolve, right? So this also has some problems with it. Problems or disadvantages of hill climbing. So let's just check. It checks local maxima. The first problem is local maximum. That means this thing that I made you understand earlier, that if we have a graph representation, if we have a graph representation over here like this, then it will find the local maximum, that is, it will find a solution and then quit the algorithm, and it will not go for the global maximum, that is finding the optimum solution. Okay, so that is one of the problems, because we want optimum solution. So we only get the local maxima and not the global maximum. Okay, that is one thing. Then second thing is, what if we have a plateau or ridge? So what does it mean? That here we have slopes, right? Like this, we have slopes. Sorry for my drawing, but we have slopes over there. What if I have like this? I have a flat surface and then a declination. So all these points over here, all these points are local maxima of that. Like if I have a graph over here, I'll just draw it a bit neatly. Say for example, I have a graph over here and I have like this ridge, like a plateau, and then a steep down over here. Then all these points are at a common parallel line, then all will be local maxima. Then how will the computer decide which one is the answer? Because this is also correct, this is also correct, this is also, all are local maxima only. So that is one of the problem where the computer makes, like the system makes problems while using hill climbing. Then we have ridge, flat surfaces. Ridge, I'll just say, sorry, here no, it's ridge. Ridge I'll discuss. Ridge is the special case of local maxima, but here it is plateau or flat surface. Either it's a plateau, like plateau is like this, flat mountains, or it's just a flat surface. Third one is ridge. Now ridge is a special case of local maximum. What do I mean by this? That just need a space. I'll just draw it over here in the corner down. So if I have a graph like this, okay, this is x-axis, this is y-axis, and we have a z-axis. That is, we are drawing in 3D space. Then what happens is, if I have like this, okay, this point over here, it's not flat, it's not plateau also, but we have more than one points over here. A typical line of points are local maxima. So that is also a problem while solving hill climbing, which can be faced. That is, now this is known as a ridge, that you have a series like a wall of plateau or wall of points which are same. Okay, so this is a ridge. So that's full is a ridge. That's a case. That's where we have problem solving this. So this was all about hill climbing. Okay, so till now let's just quickly revise. So hill climbing, we saw that it's called local search algorithm. It uses greedy approach and there is no backtracking. And then we evaluate the initial states and loop until the solution is found or there are no more operators left with us in the problem. We select and apply the new operator and then evaluate the new state till we find the goal state, then we'll quit. Otherwise, if the next state, that is the next state, if it is better than the current state, then the next state will become the current state. Like step by step, we will climb the hill. And if we have reached the local maximum of the hill, we'll quit the algorithm because we found the local maximum. Now, it will find a solution, but it will not find the optimum solution. So what are the problems of hill climbing is that it will find only the local maximum. Then if we have plateau or a flat surface, then we'll have problem finding local maximum because there will be more than one local maximum present because all will be at the same height. Then similar is the case with the ridge, which is special case of local maximum. So all these were the problems while solving a hill climbing problem. So this is all for hill climbing. Thank you for watching this video. Please stay tuned for more such content to Techno. Also do like, share and subscribe our channel and press the bell button to get the latest video updates to our channel. Thank you.